Hello, welcome to In 5 Minutes. The most important concept here is the DC load line. Now to just refresh the concepts, to identify this type of transistor. This transistor which is given is NPN or PNP. As I have told you, arrow marks the P and N direction. So arrow is always from P to N. So this is P, this is N, and other side is N. So this is an NPN transistor. Right now, how to identify the various terminals? I mean to say whether it is common base, common emitter and common collector. Once you identify the terminals, you can easily identify whether it is common emitter, common base or common collector. Now this arrow is from base to emitter, right? So this is your emitter, this is your base and this is your collector. Now over here, if you see, this is your emitter, this is base and this is collector. This is your input port and this is your output port. So you have total how many terminals in the device? You have terminal 1, terminal 2, terminal 3. So BJT is a 3 terminal device. And how many ports? It has 2 ports, one input port and one output port. Now which terminal is common to input port and output port? You can see emitter is common to base and emitter is common to collector. So this configuration is nothing but a common emitter NPN transistor configuration. Now how to identify whether it is operating in active region, cutoff region or saturation region? I have told you, whenever you have a transistor, just draw a diode like this over here, like this over here. If P is connected to positive and negative, and here negative is connected to the positive terminal in this fashion, and over here positive negative, that means JBE is forward bias, this is JBE, and JBC is reverse bias. That means the transistor is operating in the active region. If I am drawing a diode over here and a diode over here, right? Positive, negative. Positive is connected to plus VBB, negative is connected to negative of VBB. Negative is connected to positive. So what you can say, the transistor over here is operating in active region. What is the application if the transistor is operating in active region? It is acting as an amplifier. Right, this is the basics of the circuit given. Now we will move to the DC load line. Now when you look at the diagram, what are these all components? Why we have VCC, why we have VBB, what are their importance? As I have told you, VBB and VCC are used to keep the transistor in the active region. So that is the significance of the externally biasing voltages VBB and VCC. Right, then you have RB. This resistance is RB and this resistance is RC. The resistance in the base is RB and the resistance in the collector is RC. Why we use RB? RB used to limit the base current in microampere and to provide adequate voltage to keep JBE, that is this junction, forward biased. What is the purpose of RC? RC is used to convert the output current to output voltage. So if you want the output current to be converted to voltage, then what you will have? You will have RC in the circuit. These are the significance of all the components used in the circuit. Then this condition wherein only DC voltages are applied to the transistor, that is VCC and VBB, then this condition is called as quiescent condition. Right? Why we do the DC load line analysis? So we can find the maximum DC voltage and current that can be handled by the transistor. Now to start with the analysis, if you apply KVL to the collector loop, this is your collector, this is your base and this is your emitter. So applying KVL to collector emitter loop. So what will be the equation if you apply KVL to collector emitter loop? Starting from this point, we are living with a positive sign, so plus VCC. Here positive negative, we are living with a negative sign, so minus IC into RC. Then plus minus VCE, we are living with negative sign, so minus VCE equals to 0, right? If I am rearranging the equation, ICRC if I am taking on the other side, what I will have in the equation, ICRC equals to VCC minus VCE. So if I am writing IC equals to VCC upon RC minus VCE upon RC. Now if you look over here, VCC is the externally connected voltage. So it is a constant. This part I can call it as constant because RC is externally connected resistance whose value will not change. Again VCC is externally connected voltage whose value we are not changing. So you can call it as a constant. So I can again rearrange it and I can write it as IC equals to minus VCE upon RC plus VCC upon RC.